Hello everyone, thanks to everyone for watching this video. My name is Qida. I am an architect and engineer. Today's video is titled Fluid Kinematics, and it is going to provide you a broad overview of velocity field and also the Reynolds transport theorem. I'm going to give you an overview of what I'm covering today's video. In this video, we will discuss various aspects of fluid motion without being concerned with the actual forces necessary to produce the motion. That is, we will consider the kinematics of the motion, the velocity and the Reynolds transform theorem of the fluid, and the description and visualization of its motion, then wrap up with conclusions. In general, fluid flow, that is, there is a net motion of molecules from one point in space to another point as a function of time. We employ the continuum hypothesis and consider fluids to be made up of fluid particles that interact with each other and with their surroundings, each particle rather than individual molecules. This motion can be described in terms of the velocity of the fluid particles. The infinitesimal particles of a fluid are tightly packed together. Thus, at a given instant in time, a description of any fluid property, such as density, pressure, velocity, may be given as a function of the fluid's location. This representation of fluid parameters as functions of the spatial coordinates is termed a field representation of the flow. Of course, the specific field representation may be different at different times. So that to describe a fluid flow, we must determine the various parameters not only as a function of the spatial coordinates x, y, z for example, but also as a function of time t. Shown in the Morgan figure is one of the most important fluid variables, the velocity field, where u, v, and w are the x, y, and z components of the velocity vector. By definition, the velocity of a particle is the time rate of change of the position vector for that particle. As is illustrated in this figure, the position of particle A relative to the coordinate system is given by its position vector Ra, which if the particle is moving is a function of time. The time derivative of this position gives the velocity of the particle dRa over dt equal to Va. By writing the velocity for all of the particles, we can obtain the field description of the velocity vector v equal to vxyzt. Although fluid motion can be quite complicated, there are various concepts that can be used to help in the visualization and analysis of flow fields. There are streamlines, straight lines, and path lines. The streamline is often used in analytical work, while the straight line and path line are often used in experimental work. In this video, we focus on the streamline. A streamline is a line that is everywhere tangent to the velocity field. If the flow is steady, nothing at the fixed point, including the velocity direction, changes with time. So the streamlines are fixed lines in space. For unsteady flows, the streamlines may change shape with time. Streamlines are obtained analytically by integrating the equations defining lines tangent to the velocity field. As illustrated in the Morgan figure, for two-dimensional flows, the slope of the streamline, dy over dx, must be equal to the tangent of the angle that the velocity vector makes with the x-axis. The equation shows here. If the velocity field is known as a function of x and y and t if the flow is unsteady, this equation can be integrated to give the equation of the streamlines. We are sometimes interested in what happens to a particular part of the fluid as it moves about. Other times, we may be interested in what effect the fluid has on a particular object or volume in space as fluid interacts with it. Thus, we need to describe the laws governing fluid motion using both system concepts, consider a given mass of the fluid, and control volume concepts, consider a given volume. To do this, we need an analytical tool to shift from one representation to the other. The Reynolds transport theorem provides this tool. All physical laws are stated in terms of various physical parameters. Velocity, mass, temperature, and momentum are but a few of the more common parameters. Let capital B represent any of these or other fluid parameters, and B represent the amount of that parameter per unit mass. That is, capital B equal to m times B, where m is the mass of the portion of fluid of interest. The parameter capital B is termed an extensive property, and the parameter B is termed an intensive property. The value of capital B is directly proportional to the amount of the mass being considered, whereas the value of B is independent of the amount of mass. The amount of an extensive property that a system possesses at a given instant, B system, can be determined by adding up the amount associated with each fluid particle in the system. For infinitesimal fluid particles of size delta V bar and mass rho delta V bar, this summation takes the form of an integration over all the particles in the system and can be written as this equation. Most of the laws governing fluid motion involve the time rate of change of an extensive property of a fluid system, the rate at which the momentum of a system changes with time, the rate at which the mass of a system changes with time, and so on. Thus, we often encounter terms such as this equation. To formulate the laws into a control volume approach, we must obtain an expression for the time rate of change of an extensive property within a control volume, BCV, not within a system. This can be written as this equation, where the limits of integration, denoted by CV, cover the control volume of interest. A simple version of the Reynolds transport theorem relating system concepts to control volume concepts can be obtained easily for the one-dimensional flow through a fixed control volume, such as the variable area duct section shown in Figure A. We consider the control volume to be that stationary volume within the duct between sections 1 to 2, as indicated in Figure B. The system that we consider is that fluid occupying the control volume at some initial time t. A short time later, at time t plus delta t, the system has moved slightly to the right. The fluid particles that coincided with section 2 of the control surface at time t have moved a distance delta L2 equal to V2 times delta t to the right, where V2 is the velocity of the fluid as it passes section 2. Similarly, the fluid initially at section 1 has moved the distance delta L1 equal to V1 times delta t, where V1 is the fluid velocity at section 1. We assume the fluid flows across sections 1 and 2 in a direction normal to these surfaces, and that V1 and V2 are constant across sections 1 and 2. As is shown in Figure C, the outflow from the control volume from time t to t plus delta t is denoted as volume 2, the inflow as volume 1, and the control volume itself as CV. Thus, the system at time t consists of the fluid in section CV, that is, system equal to CV at time t. At time t plus delta t, the system consists of the same fluid that now occupies sections CV minus 1 plus 2. That is, system equal to CV minus 1 plus 2 at time t plus delta t. The control volume remains as section CV for all time. If B is an extensive parameter of the system, then the value of it for the system at time t is this equation. Since the system and the fluid within the control volume coincide at this time, its value at time t plus delta t is this equation. Thus, the change in the amount of B in the system, delta B system, in the time interval delta t divided by this time interval is given by this equation. By using the fact that at the initial time t, we have B system equal to BCV. This ungainly expression may be rearranged as shown in this equation. In the limit delta t to 0, the first term on the right-hand side of this equation is seen to be the time rate of change of the amount of B within the control volume as this expression. The third and second terms on the right-hand side of the above equation represent the rate at which the extensive parameter B flows from the control volume across control surface. They are derived as these equations. If we combine these equations, we see that the relationship between the time rate of change of B for the system and that for the control volume is given by this equation. This equation is a simplified version of the Reynolds transport theorem. We will now derive it for much more general conditions. A general fixed control volume with fluid flowing through it is shown in this figure. The flow field may be quite simple, as in the above one-dimensional flow considerations, or it may involve a quite complex, unsteady, three-dimensional situation. In any case, we again consider the system to be the fluid region 2 has excited from the control volume, and the additional fluid region 1 has entered the control volume. We consider an extensive fluid property B and seek to determine how the rate of change of B associated with the system is related to the rate of change of B within the control volume at any instant. In general, the control volume may contain more or less than one inlet and one outlet. A typical pipe system may contain several inlets and outlets, as are shown in this figure. In such instances, we think of all inlets grouped together and all outlets grouped together, at least conceptually. The term B out represents the net flow rate of the property B from the control volume. Its value can be thought of as arising from the addition, integration of the contributions through each infinitesimal area element of size delta A on the portion of the control surface dividing region 2 and the control volume. This surface is denoted CS out, as shown in this figure. Since delta L equal to V times delta T, the amount of the property B carries across the area element delta A in the time interval delta T is given by this equation. The rate at which B is carried out of the control volume across the small area element delta A, denoted delta B out, is this equation. By integrating over the entire outflow portion of the control surface, CS out, we obtain this equation. In a similar fashion, by considering the inflow portion of the control surface, CS in, as shown in this figure, we find that the inflow rate of B into the control volume is this equation. The net flow rate of parameter B across the entire control surface is this equation, where the integration is over the entire control surface. By combining the previous equations, we obtain this equation. This can be written in a slightly different form by using BCV expression, so that we obtain this equation. This equation is the general form of the Reynolds transport theorem for a fixed, non-deforming control volume. From conclusions what we learned, the concepts of a field representation of a flow are introduced. Streamlines, which are lines tangent to the velocity field, are identical to straight lines and path lines if the flow is steady. For unsteady flows, they need not be identical. The Reynolds transport theorem is developed by using these ideas. The analysis of flows can be carried out using a control volume, a volume usually fluid, through which the fluid flows. Whereas the governing principles are stated in terms of a system, a flowing portion of fluid. Okay, thanks to everyone for watching my video today, and I do hope you found the video informative, and that you learned some things from it. If you do have any questions, then you can write comments and messages. I am happy to answer any questions. Thanks for your watching.